Welcome back everyone. In this lecture we will see a proof of this sure orthogonality relations. So, for that like I said we need to do some preparations. So, let us begin with those preparations. So, let us fix some notations. So, we will actually work with the following representations v comma phi and w comma rho, and let us fix the dimension of v to be n and then dimension of w to be m. So, now by fixing a basis of v and w, so we will be able to actually identify the home space v comma w to this set of all m by n matrices. So, now we want to do everything into all computations in terms of these matrices. So, for that purpose we need to actually understand the projection map P that we defined as a function on this matrix space. Okay. In order to understand how that projection works on this, so let us try to understand how that works on the standard basis. So, let us fix this standard basis E I j of this m by n matrices, where note that I runs over 1 to m, there are m rows and then n columns. So, what is this E I j? So, this E I j is the m by n matrix so with 1 in position I j. So, with the entry I jth entry is 1 and then 0 elsewhere. Okay. So, that is how the standard basis of this set of all m by n matrices obtained. So, now what we want to do? We want to actually understand this projection map P that we define from this home space to home space. So, recall that. So, this function P is a linear function that is defined from this home space to home space. So, now what we want to do? We want to identify this home space as this space of m by n matrices. So, P can be thought of a map linear map from this m by n matrix space to m by n matrices. So, now recall how we defined this T hashtag. So, the T hashtag was given by 1 divided by the cardinality of G summation rho G inverse T phi G G in G. So, in this actually we can see that this T hashtag is actually sum of some other functions. Okay. So, basically we have these other functions. Okay, let me call it. So, given A and B, you have this function pi A B, again it is defined from this m by n matrices to m by n matrices as follows. You take the matrix x to A x B. So, this is indeed a linear function from the space of matrices to space of matrices, and you can see that this one looks exactly like pi rho G inverse phi G. So, this is exactly pi rho G inverse gamma phi G. So, basically this map P is indeed sum of these maps. So, P of T is T hashtag. So, the P is nothing but summation over G in G pi of rho G inverse gamma phi G. So, this suggests that in order to understand P, recall that we wanted to take the trace of P. So, for that purpose we need to actually understand how to take trace of these individual operators pi a comma b. So, let us try to understand how to work with this maps pi a comma b. So, for that purpose let us actually do the computation very explicitly. So, if we want to actually compute, okay, so let us say you have this map pi a comma b, which is actually map from this m by n matrices to m by n matrices. So, if you want to actually find out what will be the trace of this pi a b, then we have to work with this standard basis E I j, and then we need to compute what will be the image of this pi a b E I j, and then we need to write it down in terms of this E r s with some coefficients, let us say A r s. So, then the matrix of this pi a b becomes this big m by m n times m n times m n matrix. So, where you will have this A r s. Okay. So, the positions in this matrix, so they will be indexed by this r s comma I j. So, then you will be able to see. So, let me use this notation that the entry corresponding to this position r s comma I j is going to be exactly this entry. Okay. So, to be actually somewhat more accessible, let us recall how we are going to write down the matrix of T with respect to some basis. So, if we take T is a linear map from V to W, so then if we fix the basis of V 1 etcetera V n, this is the basis of V. So, then all we do is we compute T V j, and then we write this as summation A I j W I, where W 1 etcetera W m. So, this is the basis of W. So, this is basis and this is also basis. So, then you can write down the matrix of T with respect to these bases as this A I j. So, you can see that this is indeed m by n matrix. So, that is what we are going to do with for this operator pi a b with respect to this basis E I j. Okay. So, that means the indexing set for this matrix itself is the product of this tuples r s I j. So, that means this r s comma I jth entry. So, that is going to be exactly this A I j comma r s or A I j comma r s. So, that is how we will be able to compute. So, then the trace of this operator is going to be sum of the diagonal entries. So, where I j becomes equal to r s. So, that is how we will be able to compute the trace. So, basically we are going one level up, we are working with matrix space and operators on the matrix space. So, it is expected that the computations will be little difficult. Okay. So, to understand this, let us do these computations slowly and step by step. So, for that purpose let me actually state this lemma where the matrix computation is explicitly given. So, let me actually fix the sizes of the matrices. So, let A be R by M matrix and then B by N by S matrix. So, then we have this EKI which is the elementary matrix which is in M by N matrix space. So, given this we want to compute what will happen to A EKIB. So, then if I compute A EKIB and then look at its LJth entry, because this is going to be a matrix. So, see that A is R by M matrix and then we have EKI is M by N matrix and then B is nothing but N by S matrix, N by S matrix. So, this resulted product A EKI B is going to be product of this. So, this is going to be exactly R by S matrix. So, in that R by S matrix we are computing this LJth entry and one can prove that this LJth entry is going to be the product. So, this is going to be product ALK times BIJ. So, where we use this notation A is given by AIJ and B is given by BIJ. Okay. So, this is what we get when we look at this LJth. So, this is basically just matrix multiplication, but in order to be sure let us try to prove this. So, here is the proof. So, if we compute these products in terms of definition, you can see that A EKI B LJ. So, all I am doing is matrix multiplication. So, then this is going to be exactly summation A LX EKI XY and then B YJ, where x y runs in respective sets. But we know something about this entry. So, EKI the xy entry is going to be exactly 1 whenever ki equal to xy, otherwise it is going to be 0. So, when ki is same as xy, so then only this EKI xyth entry is going to be 1, or otherwise it is going to be 0. So, that means, so this sum is going to be exactly equal to summation. So, now okay, the xy takes exact value k and I. So, there is no summation. So, this is exactly A L x is going to be k and then this entry is going to be 1 and this B yj is going to be B ij. So, this is what we wanted to prove. So, it just follows from the matrix multiplication. So, basically we observe that this LJth entry of this A EKI B LJth entry is exactly given by A L K B I J. Okay. So, now let us actually look at the operator that I was actually promising. So, if we take this operator x goes to A x b and we want to think this is an operator from, so this is pi A b from this set of all m by n matrices to the set of all again m by n matrices. So, to match these dimensions it is clear that we have to take A to be. So, let us go back. So, we want this R to be m and then this S to be n. So, that means this is comes from m by n matrix and this comes from n by n matrix. Okay. So, this A comes from m by m matrix and then this B comes from n by n matrix. So, recall that so this A and B they comes from this rho of G inverse and phi of G. So, rho of G inverse is going to be n by n matrix, and similarly phi of G is also going to be n by n matrix. So, that is how we are actually having this. So, we want to understand what happens to this pi a b. So, if we go through the computation, we can see that we are interested in this pi a b of x, which is a x b. So, when you look at a e k I b, then the LJth entry is exactly given by a l k and then b I j. So, that means if we write down the matrix of this operator pi a b. So, you can see that. So, this pi a b of x, which is exactly given by a x b. So, this if you rewrite in terms of E L j, linear combination of E L j. So, that is going to be the LJth. So, that is So, we want to write down A x b in terms of the linear combination of basis, then we will be able to compute E k I comma L jth entry. So, then you can see that this is going to be the coefficient of E L j is exactly A L k b I j. So, this is the coefficient. So, that means, so this is exactly equal to that L j comma k ith entry in the matrix of this pi a b. So, that means, so what will be the trace of this? The trace of this pi a b. So, we need to sum the diagonal entries, sum diagonal entries. So, you can see that the diagonal entries obtained by being this L j, this tuple is same as k I. So, that means L should be equal to k and j should be equal to I. So, you can see that means this is exactly sum of A L L and then B I I, where L and I runs over. So, then this is exactly going to be sum of A L L times summation B I I. So, this is something looks familiar. So, basically this is the trace of A and then this is trace of B. So, basically the trace of this operator by A B given by the product of this trace. So, this is indeed very useful, because recall that we had this operator P which is defined from this home C v comma W to the home C v comma W, and which was given by T goes to T hashtag. So, which is exactly the summation G in G rho G inverse T phi G. So, that means the trace of this operator P is exactly sum of the traces of this individual operators. So, you can see that summation 1 divided by the cardinality of G, G in G, pi of rho G inverse comma phi G. So, the trace of these operators. But what is the trace of this operator? Just now we have seen. So, this is going to be exactly the trace of this rho G inverse times the trace of phi G. But this something looks very familiar. So, this is basically the character value. So, basically the trace of P is given by 1 divided by G summation chi. So, let me so summation G in G, and you have this trace of rho G inverse and then the trace of phi G. So, let me just write it as it is. So, basically this is chi rho of G inverse and then this is chi phi of G. But when we work with unitary operators, suppose this rho is unitary, then we know that rho of G inverse is supposed to be rho of G adjoint. So, that means this trace of this rho of G inverse is going to be the trace of rho G bar. So, now using this you can see that the trace of P is exactly 1 divided by the cardinality of G summation chi rho of G bar chi phi of G in G. So, here we assume that rho is indeed unitary. So, that is something we can assume because up to equivalence we can choose always unitary operators. But this is something looks very familiar to us. So, basically this is indeed the inner product that is given inside CG. So, for given F1 and F2 in CG, so the inner product of F1 F2 has exactly this formula. So, that means the trace of P is exactly given by the inner product chi phi divided by chi rho. But on the other hand, the trace is already we know. So, this is nothing but the dimension of this home G v comma w. So, now using this observation we can see that so we have chi phi comma chi rho is exactly the inner product is equal to dimension home G v comma w. So, now if we assume that both v and w are irreducible unitary representations, then using Schur's lemma, so we will be able to immediately get first orthogonality relations. So, here is first orthogonality relations. So, this is actually tells something about the irreducible characters. Okay. So, we take rho comma phi, both are irreducible unitary representations of G. So, then we have this equation. So, then from this equation and Schur's lemma, you can see that the inner product is exactly 1 if phi and rho are equivalent and 0 otherwise, because this home space exactly behaves that way. And then this irreducible character, they are unique up to equivalence. So, when phi and rho are equivalent, we can pick rho to be unitary representation that is equivalent to phi. So, then we can compute this okay. So, I guess we do not need this unitary here, we can just simply take irreducible representations of G. So, then what we can do when phi is equivalent to rho, you just pick rho to be unitary, then we have this equality, but we know that home G v comma w is 0, sorry home G v comma w is one dimensional in that case. So, we get this first equality, and for the second equality anyway, when phi and rho are not equivalent, when phi is not equivalent to rho, So, then this home G v comma w is going to be 0. So, that is going to give us that this inner product is 0. So, basically it proves that when you take chi rho, where rho comes from inequivalent, rho is just irreducible. So, we can also take it to be unitary, there is no harm in that, because whenever we take isomorphism class of representation, we will be able to pick always one unitary representation there. So, then if we take inequivalent set of irreducible representations, okay. So, let me make some notation. So, let us call this capital lambda the set of all inequivalent irreducible representations of G, then basically we are taking this chi rho from chi rho where rho runs over this capital lambda. Then we just proved that as an as a subset of this CG. So, this is indeed orthogonal. Actually, it is orthonormal because that is what our computation says. So, this is indeed. So, let us rewrite this. So, this is indeed orthonormal set. Now, note that this set chi rho, rho in lambda. So, this lives inside this space of class functions, and since it is indeed orthonormal subset. So, that means the cardinality of this chi rho and then rho in lambda. So, this is going to be at most the dimension of this space, dimension of this CG. So, which is exactly the number of conjugacy classes. So, we get two immediate corollaries. One is the number of inequivalent irreducible representations. So, that is finite, and that number is going to be at most the number of conjugacy classes of G. Indeed, later we will prove that the number of conjugacy classes is going to be exactly equal to the number of inequivalent irreducible representations of G. So, for that again we need to do little bit more preparations, but anyway that is something that we will actually see it in the future. But this is something we proved without actually using the matrix coefficients. But what can we say about the matrix coefficients? If you think about it, the connections between the matrix coefficients and this projection map P is recorded in the following lemma. So, let me just state this lemma and then stop. So, here is the lemma. So, now we take phi and rho both to be unitary irreducible, sorry, we do not need to assume irreducible, we just take unitary representations of G. So, then we simply take A to be this standard basis element EKI. So, which we are going to think it as operator on this home v comma w. So, this is nothing but home v comma w. So, now what we are going to do, we are going to look at what happens to this operator when we apply this P. That means we want to compute this A hashtag. So, computing A hashtag is same as computing its LJth matrix entry. You can see that. So, this is going to be exactly equal to the inner product between these matrix coefficients phi ij and rho kl. So, maybe we do not need to use this A. So, let us write it. So, this E k I hashtag LJth entry is going to be the inner product between this phi ij and rho k. So, then using this observation we will be able to actually prove the orthogonality relations between this phi I j and rho k l. So, that is the Schur's orthogonality relations that we can prove later. Okay, I will stop here and then we will continue with the proof of this orthogonality relations in the next class. Thank you.